The talk in this session is given by Nathan Schwadron. It's LRO Crater Discoveries of the Lunar Radiation Environment and Lunar Regolith Alteration by Radiation.
Great, thanks a lot. So I'm going to talk about three themes today. LRO Crater started as an instrument to detect radiation, and it's really become, I think, a very rich experiment that's exposed a lot of new elements of what we understand and don't understand about the regolith. And I'm going to come today about it to a discovery, a huge surprise that we've made over the last year with respect to our understanding of the regolith. So this is kind of an anniversary for us. We just hit the mark of more than 50 refereed publications. We're probably going to be, by the end of the year, we'll be closer to more than 55 or 60 refereed publications from the Crater team in human exploration, heliophysics, and planetary science. It's been a really fun and rich go. The Crater special issue in space weather came out last year. We have a number of articles on charging the regolith and changing space environment, and articles on the proton albedo and its implications, and that's kind of where the surprise comes, which I'll talk about in a second. So really the talk is devoted to these three themes. First of all, we're seeing a radically different radiation environment than really has ever been explored in the space age. We're even seeing events that just happened about a month ago, which are continuing to change our perception of how the solar cycle actually works. We've been working on lunar surface charging and dielectric breakdown, some pretty significant surprises there. Andrew is going to be speaking about that later today. And then new insights on the energetic proton albedo. Remarkable new insights that are coming out. Again, I'll talk more about that later in the talk. That's kind of the big surprise. So this is the solar cycle. This is the complete record. This is the dose rate that we see from the Crater instrument over the entire mission. Basically, the bottom line is we're seeing a much quieter sun than we've seen throughout the entire space age. Relatively few and weak solar energetic particle events, very, very high fluxes of galactic cosmic rays. It's a very different sun than we've been used to for the last 50 years. And if you look at the solar cycle, you sort of see that things are sort of winding down towards solar minimum. And sure enough, right here, we see an event that's one of the largest events that we've seen throughout the entire solar cycle coming in solar minimum. This was seen in the very early days of some of the first solar cycles that we detected, a sense that during weak solar cycles they can still produce strong energetic particle events even in the declining phase. This is kind of a close-up on that event. It's kind of amazing. The sun is doing exactly what we've seen in historic data, but we've never actually seen it up close with this type of instrumentation. When we look at predictions towards the future, we see predictions of a continual rise in galactic cosmic ray fluxes towards the next solar minimum. This is becoming a factor for human exploration because the increased radiation that we're seeing from deep space actually limits the amount of time that astronauts can spend in deep space. So the reductions of solar activity have real implications. In this case, we're seeing typical time periods for a 30-year-old astronaut is getting to sort of less than a year in deep space, even behind good amounts of shielding. So that becomes a limiting factor in human exploration. It's something we need to pay attention to and continue to try to understand. The probability of events, extremely low throughout the cycle. This is the probability as a function of blood-forming organ dose. You can see that the 30-day, one-year limits for SEP events are up here. The probability is extremely low, very, very weak events in the cycle, by far the weakest cycle that we've seen throughout the entire space age. But again, the sun is not done yet. It may be that we continue to see very strong events in this declining phase. So the sun is continuing to turn up some pretty significant surprises. Okay, so this is Andrew's work, and he's going to be talking about this, Andrew Jordan. He's going to be talking about this later today. But the bottom line is that what we're seeing in terms of the energy flux from solar energetic particle events and the very, very low conductivities that we have in permanently shaded regions leads to a situation where when you do have solar energetic particle events, you actually lead to a discharging process that leads to significant amounts of vapor and melt production. And ultimately, if you compare that between meteorites and this new breakdown process, you find that it's comparable or even larger in terms of vapor and melt production than meteoritic processes. So this is telling us that the garden soil in permanently shaded craters breakdown is likely to be a very, very big part of that story. So the way this works, of course, you've got regolith. This is a grain at sort of the regolith surface. Suddenly you have a solar energetic particle event that leads to the buildup of an electric field due to charge separation. That finally, because of the low conductivities, that can lead to a discharge event. Discharge event leads to a breakdown, typically at grain boundaries, the generation of vapor, and then finally the grain fragments sort of move around, leading to this sort of fluffy regolith. Now, one of the things that we saw in Paul's talk yesterday was the fact that because of the low thermal conductivities in the surface, you can achieve huge gradients, even over centimeter scales. And he was talking about lateral gradients. It immediately made me think about the situations here where even if you have a region that is not in shadow, which is exposed to light, these regions can still house very large subsurface gradients, leading to making these regions likely places to house volatiles. So that's a pretty significant process. This also is going to change the reflectance albedo, the actual light albedo, not the energetic particle albedo, in PSRs, and that's a process that we're starting to really dig into now, and we're starting to discover some new things. So stay tuned for some aspects of that. This comes from a discovery that we made quite early on, and this is where we started to get into, with the crater instrument, started to look at the types of doses that we were getting, and we realized that the amount of doses were so large that it was very likely that we were seeing significant amounts of chemical alteration in the subsurface regolith. In this case, it likely explains the amount of H2 that was observed by LAMP after the L-cross impact. We find that over 1 billion years, the process of radiation chemical alteration leads to a process of breakdown of water and the buildup of H2 that likely explains those observations. And this work was actually motivated by a comment that Mike Wargo made during one of my early talks. So this work is really directly thanks to Mike. Okay, now this gets into some of the surprises we've been making. So over the last 3 years, we've been doing a series of beam runs to try to understand what we would expect in terms of the radiation albedo. How does it depend on chemical composition of the surface? So we've done experiments. We've taken a beam, shot it at regolith simulant, and taken the crater instrument in the lab to see exactly, how the radiation albedo depends on the composition of material. Okay, so basically what we find is a confirmation of the obvious thing, nuclear evaporation and forward scattering. And the basic idea is that the more heavy elements that you're going to have, the higher the average mass within material, the more that material, when it gets hit by radiation, it essentially absorbs that energy and it radiates nucleons in all directions. The higher the average mass, the more secondary radiation is going to be generated, and as a result, the higher the radiation albedo that you should see, the proton albedo you should see. Conversely, if you start to implant material with hydrogen or water or OH, whatever, that is going to lower the average elemental mass within that material, and it's going to lead to more forward scattering. So when you have parent particles that come in, as opposed to this chemical process where you absorb the radiation and emit secondaries in all directions, instead you get more secondary scattering into the regolith, which leads to a suppression of the proton albedo. So you have two predictions coming out of this. One is that higher average nucleon mass, higher mass density within albedo should lead to increased proton albedo. The presence of hydrogen in the regolith should decrease the proton albedo. So that's something, those are very simple signatures that we can go and search for. And sure enough, if you take a look at, and these are results of the maps, you can see a poster on this from Jody, but basically over the course of time we can really resolve the differences. In this case, this is shown The resolved differences is a function of time as we get better and better statistics. But the bottom line is that the Maria is a much higher emitter of albedo than the Hyalins. And it's a real statistical difference there. And the Maria, of course, has higher average atomic mass enriched in things like iron and titanium. The Hyalins lower average atomic mass because of the history and the fact that that's sort of the Hyaline Maria is more basaltic material. So the bottom line is that the first of those predictions is clearly confirmed. You see a real difference. These regions that are more emissive are going to be regions of higher mass. Okay, now the interesting thing as you continue to resolve these albedo proton maps, you start to see these bright hotspots. The bright hotspots are not necessarily linked to high titanium abundances or high iron abundances as far as we can tell. But it may be that there's other reasons that those regions are higher average mass. That's the best hypothesis going forward. This shows a collection of different hypotheses that we've looked for, but the bottom line is nothing has really correlated all that well. So the bottom line is that these bright spots are still to some extent a mystery. But that's not the big mystery. The big mystery comes when you start to look at the latitude distribution of the proton albedo. So remember the second prediction that I made. The prediction was that the presence of hydrogen should suppress the proton albedo. You should see a suppression then of the proton albedo as you go from high latitudes compared to low latitudes. And this is the trend that you see. We could not really resolve this trend statistically until very recently. We now have the statistics to really say this definitively. And what we find is that there's clearly a gradient, and it's the opposite gradient than what you expect. The proton albedo yield is higher at high latitudes compared to low latitudes. And this, when we finally saw it and resolved it and we realized that we couldn't get away from this conclusion, we started scratching our heads vigorously. One of the things that we came up with is the fact that the nuclear evaporation process in the regolith is going to produce more secondary neutrons. If there's a hydrated layer at the surface, those secondary neutrons are going to convert into protons. So the bottom line is we think that this is evidence of a 1 to 10 centimeter layer of hydrated material that's richer in hydrated material near the surface. You can actually use this to estimate essentially that enhancement of albedo at high latitudes is about 1%. You can use that to estimate the column densities. If you have a 20 centimeter layer, you get hydrogen enhanced by about 200 parts per million, which is more or less consistent with the ranges that have been observed in cold traps. That albedo really matters. That albedo is also a significant hazard for humans if they return to the moon, because essentially you have radiation coming not only from above, but also back from below. And those secondary neutrons and those protons do a lot of biological damage. So I'll end there. The three main points you can see here: very deep solar minimum, a lot of surprises there. Radiation effects from the moon, seeing chemical alteration, combined with deep dielectric charging and discharging that's leading to changes in the properties of the regolith. And finally, huge surprises in the proton albedo and what we think is evidence of a surface hydrated layer.
We have time for maybe one question. I did have one question. You go all the way back to a comparison of the solar cycle and galactic cosmic radars.
Yep.
Fairly far to the beginning. Comparison between the model. This.
Right.
There's a slight offset, with a phase shift between the minimum in the model and the apparent peak in the sunspot number. Do you know why that might be?
Yeah, that's pretty well known. When you have changes in sunspots, that's going to change the properties of the the solar wind that's coming out. But then it takes a year to get out through the solar system, and then it's going to take even more time to get out through the heliosheath. The heliosheath is the thing that's primarily doing the modulating. Sort of 80% of the modulating. So that's what leads to that offset.